All right, welcome back, and now we're going to talk about hormones and their role in feeding, and later on we'll continue their role in stress, right? So, we're thinking about feeding, right? The main thing that has to happen is that we want signals to go from the parts of our bodies that are digesting to say, was that enough food or wasn't it? Should we eat more or shouldn't we? And we just go back and forth. Your brain should also take in signals from sort of the rest of their body saying, do you have enough nutrition? You good? If not, let's go get some food, right? So the idea here, the main nerve pathways are you have your vagus nerve, because it conveys information up from your stomach saying is it stretching, right? If your stomach is literally stretching and full, it should be, you should be set with food, right? And then you have your splenic nerve that contains information in regards to the nutrients of your stomach. So if you remember when we were talking about the other senses you have, and you have these interoreceptors, so you have sensors in your stomach that are also sensing how much fats and sugars and different things you're getting, and those are sending signals via the splenic nerve to your brain to say, oh, we have enough fat, we have enough this. And that's why, at least the thought is, this is hard to prove, that sometimes you maybe crave a certain type of food over another. And it's literally your sort of stomach is saying that. We need this, we need that, right? So, a lot of different hormones involved here. We won't cover all of these. We'll just focus on a couple of them. But in different parts of your digestive system, there are different hormones being sent, right? So, your duodenum, that's the beginning of your small intestines, sends OEA and CCK. We're not going to spend any time on those, but these are signals that relate back to, are you getting the right types of nutrients? Your pancreas, you should be maybe not very familiar, but you should be aware of these because this is the key organ involved in diabetes, right, and regulation of sugar. And so insulin and glucagon are the main hormones there. Fat cells release a hormone called leptin. So the idea is here that leptin should tell you that you're full. So if you have more fat cells, it should be the idea to say we don't need as much. And stomach is releasing ghrelin to tell you if you need to eat. Right? So let's look at those, the pancreatic hormones in relation to controlling sugar, right? So the idea is the pancreas, right, that produces and releases insulin hormone. And I will say here, this example doesn't actually include the brain, so I'm never sure if it should, but it's just a nice example of hormonal regulation and how homeostasis should work. So the pancreas releases insulin, which tells cells in your body, particularly your liver, to take up more glucose, right? And that's basically what's happening right after eating. The idea is if your blood sugar level goes down, then the pancreas releases glucagon, and this goes to the liver to say, all that sugar that you were storing as glycogen, why don't you go ahead and release that now? Let's get the level of sugar in the blood up to the normal level. So 90 milligrams of glucose per 100 mils of blood, that's the normal level. And the idea is sort of bouncing back between these two pathways. You want to keep this roughly here. We vary a little bit. If after fasting, I think this goes down closer to 70. Certainly, if you just demolish that box of Oreos, that's going to be considerably higher too. But this is what your body is trying to do, is stay right here. And what happens is, in diabetes, you can have a couple things. Either your pancreas fails to produce insulin, which means that your body stops really storing glucose appropriately. This can lead to huge levels of sugar, and that is bad in sort of a neuroscience way, because basically, either one of these, you can go into a diabetic coma. So too much sugar, the first big effect you can have is that it starts to kill neurons. Way too much sugar kills neurons, right? And that leads you to go into a diabetic coma, and hopefully, you can be revived from that. But if you've ever heard the idea that people with diabetes have to be worried about sort of losing sensation in their hands and feet, and actually you can lose vision from this as well. There's a couple reasons for that, but one of them is called diabetic neuropathy, and this is basically the idea that too much sugar is toxic to neurons, specifically more so than other cells. So you literally can start killing your neurons by doing this. Right. So leptin. right? Leptin, remembering, back here, right? Leptin is produced by fat cells. So the idea here is that mice that lack the ability to make the leptin hormone, or a leptin knockout mice, get real fat. So that's what we're looking at here. Right on the right here is a normal mouse, and this is a mouse that can't make leptin. So leptin is supposed to be the signal that if you have a whole bunch of fat cells, which obviously this guy here does, it should be telling you not to eat, but he's not getting that signal, right? So the more fat you have, you should produce more leptin to tell you to stop eating. And this is a nice feedback pathway, right? If you eat less, you should get fewer fat cells, produce less leptin, then you could potentially be more hungry again, and you should need to find this balance, right? Unfortunately, then, this should lead to like a weight loss thing, right? We should just be able to inject humans with leptin, and they should lose weight because they won't be hungry. But for whatever reason, that doesn't seem to work. It's also not very easy because, remember, hormones have to get into your bloodstream. So literally, you would have to take injections. You couldn't just take a pill to increase your leptin levels. So why is it so hard to lose weight if you've got this, right? Why, like, this seems like this should just work, and why doesn't it? Well, that's complicated, I would say, and as this figure shows a little bit. But the main idea is you basically adjust, right? So if you chronic overnutrition, that's like the nice way of saying like you're eating too much, right? Eventually, you have a whole bunch of different things, but you see here this concept of leptin and also sort of insulin resistance, right? This is very similar to the accommodation we talked about with sort of illegal drugs, right? Or alcohol or anything, right? If you at first you have a little bit and that has an effect, and then you begin to tolerate, or tolerance is right, another word there. So then you need more and more to have the same effect. Well, that's what happens here when you start to get sort of outside of the bounds of normal, is that your body needs more leptin to get the same response, even though, you should be potentially eating less, right? The good news here, and at least from this figure, this isn't foolproof, is that you can sort of reverse this pathway with exercise. So basically, putting in exercise kind of reverses a lot of the same pathways leading to leptin insulin sensitivity. So now actually exercising, sort of counterintuitive, you would think exercise is going to make you want to eat more, and certainly your body does respond that way to a degree. You need to replace somewhat of what you've used, but also it'll change sort of your sensitivity to these different hormones and make it so that you won't quite eat as much as you used to. And that should bring you back into balance. Now, that's not a quick fix. It's not like, oh, I'm overweight, I can go for a run today and now everything's back in balance. Your hormonal pathways are meant to be sort of steady, and because of that, they're slow and they don't change that quickly. So to really get this to reset, you're usually looking to months, if not years. And I don't know if anybody ever has watched the show. It's The Biggest Loser, right? The one where they take very overweight people and they put them through training and they lose a lot of weight. Well, people have followed up those studies, or those people, and nearly, it's something like 90+% of them within the year are back to their previous weight. And this is probably a big reason, right? We can lose the weight, we know how to do it, but getting your body to fully reset, that takes probably years, especially for somebody who's been considerably overweight for a long time to get back to where it was. So, for diet and exercise, I think the key is sort of moderation and persistence, and expect slow changes, not quick changes. Ghrelin is the sort of opposite of leptin in a lot of ways. It's the signal that's released by the stomach during food deprivation. It's the hunger signal, right? Interesting, it also acts on the hippocampus during to enhance learning, which we know we're talking about, right? So this is a semi-complicated diagram. I believe it's actually from your textbook to show how these different hormones work on the brain. But the main thing is, if we're looking here, we're looking at basically the hypothalamus, right, in different areas, and you can see that these hormones are providing input signals at different spots here to basically work on two output areas. That's basically either telling you to eat or not to eat, right? So So this increases feeding down here and decreases up here. Right? That should be the key thing. So you have satiety motivate signals saying that you're full. Glucose, CCK is one of those from the duodenum we didn't cover. Insulin, and then looking at leptin as well, and then sort of hunger motivated signals like ghrelin that tell you to eat. And these go through the paraventricular nucleus. They start basically nearest the pituitary gland, go to the paraventricular nucleus of the hypothalamus, and then increase arousal, which is basically a way to say use the energy you have, or increase feeding, which means get the energy that you need. We'll come back to that in class. Here is simply, that is a nice sort of wire diagram video. This shows you where everything is sort of more specifically, where you're seeing the role of the pituitary gland together with the hypothalamus, pituitary gland down here. You're getting these hormone signals coming in to these different nuclei in the hypothalamus. Right. So some cases where these kind of don't work correctly, and we don't completely understand them, but this is the generalist is Prader-Willi syndrome. I don't know if you're familiar with that, but it's characterized by compulsive overeating, poor muscle tone, and some intellectual defect. So these are kids, they talk about they literally have to put locks on the sort of food because they can't physically stop them from eating. This is going to go over most of your heads, but I'm always fascinated. This is something we discovered sort of first in here. It's due to sort of a unique genetic abnormality. So it's a partial deletion of chromosome 15 from the father. We don't really understand why that causes Prader-Willi syndrome. But the interesting thing, or curious to me, is that if you get the same thing. So remember, we have whatever 32 chromosomes, whatever chromosomes. We get some from in one of each. They come in pairs from our mom and our dad. And so if you get this same mutation from your dad, you get Prader-Willi syndrome. If you get the same mutation, but you get it from your mom, you get something called Angelman syndrome, which is a very different disease. Nothing to do with feeding at all. Very severe intellectual deficit in these, and it's called Angelman syndrome because they're generally extremely happy kids, but a lot of times their intellectual and nervous system deficit is so strong they don't always learn to walk and things like this. So the thought is, and I think there's more than thought, that this is imprinting, or the idea of epigenetics is a real underlying cause between why this is. But it's the genes that are in these parts, it's never really 100% clear. Individuals with Prader-Willi syndrome, abnormal hypothalamus function, high levels of ghrelin, neurons that respond to satiety signals abnormally, right? All these things should have made sense. Hypothalamus is key. High ghrelin, they're basically always being told to eat, and then they're not getting the signal saying they're full. All right, so let's move into stress for a bit here, right? And I think stress is a nice, again, if we come back to this diagram here, the idea always is balance, right? We don't, just like with food, never eating is bad, always eating is bad. We have to find this middle ground. The same as with stress, right? Too little stress, we don't do anything. We don't improve ourselves. We become lazy. Too much stress, obvious big things: anxiety, fear, breakdown, burnout. Somewhere in the middle, we get sort of, and ideally sort of this yellow side, right? We get sort of the most out of ourselves, and in a healthy way, right? You need a little bit of stress to push yourself to exercise or to improve yourself or to do different things without becoming exhausted. This idea. I have no idea where people are at this time in this semester, but hopefully we're still managing to stay in the sort of yellow. All right. So how does stress work? Again, hypothalamus is the main part, and I would say the stress is sort of like, if you look at any neuroscience textbook and it is talking about hormones and behavior, it's going to greatly focus on stress and the HPA axis. So HPA is hypothalamus, pituitary, adrenal pathway, right? Let's say that, right? So cortisol is what we think of as the stress hormone, and that is released by your adrenal glands on your kidney, but it's part of a sort of circular pathway, as we'll talk more about. Release of cortisol increases metabolism, blood pressure, blood sugar, alertness, right? This is the stressed out individual we think of. right? And it inhibits the release of CRF and ACTH. So what are those? The hypothalamus releases CRF, corticotropin releasing hormone, and that acts on the pituitary gland, right, to release ACTH, which is adrenocorticotropic corticotropic hormone, right? And that in turn goes to the adrenal glands to release cortisol, whereby then cortisol goes back and turns these off, right? So the idea is that stress is meant to be temporary, right? Your brain will send a signal saying, this is a stressful situation. And that can mean something like an exam, but it also probably more long-term meant something like a predator is attacking me. I need to get out of here or figure something out in a hurry, right? So that's why alertness, blood sugar, you're all amped up to do something. But then the idea is that this should be temporary, and that's why cortisol is meant to turn off the signal once hopefully this is resolved, right? Long term, though, and this is the real problem. If you're in stress for a long time, we know that's bad. It leads to elevated cortisol leads to weight gain and atrophy of the hippocampus. That sounds bad, right? That's where our learning and memory is, right? And then interestingly, if you look at this, sleep deprivation, alcohol, and caffeine all increase cortisol levels sort of long term. So think about this in terms of the college experience, I always say here, right? Maybe things that we should change and individual change that would lead to reduced levels of stress and actually induce better performance in basically everything. How does the HPA axis and dysfunction relate to PTSD and depression? Now, these are, again, somewhat correlative, but you can sort of make sense of it. PTSD is generally actually related to low cortisol levels, which that maybe doesn't make sense, but it sort of does if you think about it, that PTSD is it's not as though these individuals are always stressed out. It's like extreme situations, right? And that's how you can see from the list. So the glucocorticoid receptors are the receptors for cortisol. So now what's happening is the idea that you have less cortisol, but anytime you get a little spike, you have the possibility of getting a major impact from that. And that seems to be one of the big things. Whereas in depression, you sort of have a little bit of the opposite, where you have high cortisol levels, high stress hormone being released, but decreased receptors for it. So basically now you're always feeling not extremely stressed out, but always but not able to feel low stress either. So you're sort of at a increased level of stress constantly, and there is, because of these high level of receptors, no way to, and a decreased level of receptors, but high level of cortisol, no way to never feel not stressed at least a little bit. All right, so that's all for this lecture. In class, we're going to discuss a few of these questions that were in the PowerPoint, but I will have a list of them for you to have thought over and have written down answers to prior to class. We'll go over the zebrafish paper, Muto et al., and discuss that figure by figure, so make sure that you're able to present those. And on Friday, we'll have neuroscience in the moves, and next week we will talk about move into neurodegenerative and psychiatric diseases. Thanks for watching.